Okay, here we go, calculus people. We got some things that we have to do today. Now what we're going to start to do is we're starting to take this idea of a derivative and we're going to apply it to something that is physics-based. And that physics-based thing is this idea of position, velocity, and acceleration. So yesterday I handed out a sheet of paper to you. So I'm going to present it right now, and then I want you to take this out. And the first thing I'd like you to do is pause the video, and then I would like you to read the top section, underlining and highlighting any of the key things that are really, really important. So stop the video now and read through the upper section. Okay, so what I'd like to do is I would like to highlight a couple of things that kind of go with this. And the first thing is this idea of displacement. Now, displacement is just simply from one spot to another, how far are those two places apart? Now, it doesn't matter how you get there. So, for example, if you drew a straight line and you were 5 meters apart, okay, your displacement is 5 meters. If you did the same thing and you went this weird curvy path and you still ended up being 5 meters apart, your displacement is 5 meters apart. So it doesn't matter what path you take when you are talking about displacement. It just matters where you start and where you finish. That key formula then is your position at one place minus your position at another. Now, the second thing that's really, really important is this thing of average velocity, okay? Average velocity is the same as the average rate of change. So you're going to notice that the formula looks very, very similar to average rate of change. Notice up here, we subtract the y's from a position graph. So we take wherever your position is, and then we divide it by the elapsed time, or the time that you kind of went through. So this formula is pretty straightforward. It's really your displacement divided by your time. And that makes sense when we talk about average rate of change. It's like miles per hour or feet per second. It's always going to be some sort of distance over some sort of time. Okay? Now, instantaneous velocity is different than average rate of change. Instantaneous velocity depends on the derivative, okay? So instantaneous velocity is the derivative of the position function, okay? So if they give you a graph that shows you the position of things, like here's where things are over a course of time, the derivative of that graph will give you the velocity at every instance. Speed is very closely related to velocity. Speed is always positive. So what we do for the speed function is we simply take the absolute value of the velocity graph. So what you do is you basically take any velocities that are negative and you make them positive. Now remember, velocity can be negative and velocity can be positive. The one thing that's nice about velocity is if it's negative, it means you are moving to the quote-unquote left or the negative side. And if it is positive, it means you are moving quote-unquote to the right or the positive side. Now, we also talked a little bit in class about this idea of a second derivative. And that is what acceleration is. Acceleration is the derivative of velocity, or it is the second derivative of position. So what that means is in order to figure out acceleration, you can either take the derivative of velocity, or you can take the second derivative of the position graph. Okay? Now, one final thing that we don't see very often, but it is occasionally used, is average acceleration. And average acceleration is the change in velocity divided by the total change in time. So what we're going to do is we're going to first of all begin by looking at these things in terms of a graph. What's happening? How is that working? Then what you're going to do is in the next video, you're going to learn how to do the math behind them. So let's start with a little problem. So let's take a look down here. You're going to notice that this problem has nothing to do with a position of velocity or an acceleration. It has everything to do with something totally different, like ice cream. So what we're going to do is we're just going to start talking a little bit about how to read function notation and how to give it kind of a label. So take a look at example 1, pause the video, read through it, and answer the questions. Okay, so an ice cream company knows that the cost C in dollars to produce Q quarts of cookie dough is this function, f of Q. Okay, now it wants you to kind of just answer a couple questions. So if f of 200 equals 70, what are the units on the 200? Well, take a look right here. The 200 represents the Q. So Q is equal to 200. So what then is the label if Q is the 200? That's going to be, as you can see, that's going to be quarts. Okay? So the 200 is quarts. Well, what is the 70? So it asks, what is the 70? Well, 70 is f of 200. So f of 200 equals 70. So that's the same thing as saying C. Okay? So C is the cost, and then it's f of 200. So it's the cost to make 200 quarts. And so 70 represents $70. Okay? So when we take a look at this and we kind of break this down, the thing in the parentheses is going to have one label, and the thing outside the parentheses, or in the equation here, is going to have another, and it's going to be clearly defined in your problem. So now, let's look at the next one. Notice there's one minor change with the next one. That minor change is this is f prime of 200 equals 3. So what are the units of the 200? Well, here's the thing. The units here are still Q. So that's still going to be 200 quarts. Okay, but here's the issue. This is f prime of 200. So what f prime is that is the instantaneous slope. Okay, so think about the graph. If we look at the graph, we have quarts down here, and we have the cost down here. So what is going to be the label of the instantaneous slope? Well, if whatever this does, we have a rise and we do have a run. Our rise is going to be cost. Our run is going to be quarts. So the instantaneous slope, it's going to be 300 or $3 per quart. Okay? Or you could write it dollars over quarts. So the instantaneous slope here is the cost per quart. So there you go. When you're looking at a problem, those are some things that you have to take into consideration, because the AP test is always going to ask you to put a label on your answers. Now, this is the big part of what we are going to do. So today we are going to take a look at how to read and understand what these graphs are doing. So how do you read a position graph? Okay, so there's a couple things you always need to note about position. The first thing that we need to know about position is we need to note that this is positive position. Okay, so what that means is when we look at position, we're always talking about an object moving in a straight line back and forth. So we have this object right down here. So positive position is going to be over here. Now, anything below it, this is a negative position. So what are you thinking about when you have a negative position? Well, if you have a start point, your negative position is always over here, negative position. So what is this object doing? Okay, so we have a position graph. So let's just give this a label of meters here, and let's give this seconds here, so we can kind of work with this. So take a look at what's going to happen. So let's talk about each section as we kind of go through this. So let's start with section number 1. It's this section. What is that object doing? Well, if we take a look at section 1, it's moving in a negative position direction, okay? And it's going to move over the course of this thing, it's going to move 4 meters in a negative direction. So it's going to go 4 meters in a negative direction. So if I was to take this object, it's going to move 4 meters in this direction. That's what it is doing for step 1. Now, let's talk about step 2. So step 2, what's going on right here? Well, in step 2, notice that it isn't changing any position. It is staying at 4 meters for 1, 2, 3 seconds. So it went I should put here that it went 4 meters in 1 second. Okay. Now, look at the other section, this next part. So for step 2, what is our particle doing? Well, step 2, it stays at 4 meters for 2 seconds. So it just sits there. Now, in step 3, we start to see some different things happening. So if we take a look at step 3, notice what's going on here. It starts moving in a very different sort of direction, okay? This means right here, from here to here, it's moving closer to the start. So what's going to happen is our object is going to move to the start, and then it's going to move 4 meters past it. So for step 3, what we are doing is we are heading 8 meters to the right over 2 seconds. So in the next 2 seconds, we move 8 meters to the right. Okay? So what you're trying to do is you're just trying to break apart what is going on here. Now, we start doing some weird things in the next sections. So I'm going to use green here, and we're going to actually, I'm going to use the lighter green. So let's call this step 4. What is going on in step 4? Well, notice your position is changing. You are getting closer or moving closer to your start line. This always represents the start of where you are. That line does. So notice we are getting closer to the start. So we move from here, we move back 2 meters. So we move back 2 meters in 2 seconds. So we move back 2 meters in 2 seconds to the start. Okay? Now, in the next section, what are we doing? Well, I'm going to use pink again. This next section, let's call it section 5. Notice what's happening. Our position is now moving away from the start line. So we are moving 1 meter in number 5. We are moving 1 meter away from the start in 2 seconds. So we now, for step 5, we're going to move 1 meter this way. And now we have our last little